Am I the only one that didn't know the incredible secrets of the life cycle of stars? Stars are born in the dense, mysterious clouds of nebulae and end their lives in explosive supernovae. But what really happens in between these monumental events? How do stars transform over billions of years, and what forces shape their destiny? Join us as we delve deep into the life cycle of stars, exploring the fascinating processes of nuclear fusion, the formation of red giants, and the creation of exotic remnants like neutron stars and black holes. Discover the secrets of the universe's most captivating phenomena and uncover the mysteries that continue to baffle astronomers today. Welcome to Astro Phantom, your portal to the unknown realms of the cosmos, where anonymity and cosmic wonders collide. Our own sun is a star, a middle-aged one at that. It has been steadily burning for billions of years, providing the light and heat that sustain life on Earth. But the sun is just one of billions upon billions of stars in our galaxy, the Milky Way. And the Milky Way itself is just one of billions of galaxies in the observable universe. The atoms in our bodies were once forged in the hearts of stars, linking us to these distant celestial objects in a profound way. Stars are not static entities, they are born, they live, and they die. Join us on a stellar journey to uncover the epic story of stars, exploring their fascinating life cycles from birth to death. Stars are born in vast, cold clouds of gas and dust scattered throughout galaxies. These clouds, known as nebulae, are often illuminated by the light of nearby stars, creating breathtaking displays of cosmic artistry. Within these stellar nurseries, gravity acts as a sculptor, slowly drawing together the diffuse material. As gravity pulls the gas and dust inward, the cloud begins to collapse under its own weight. This collapse causes the density and temperature at the center of the cloud to increase. The collapsing cloud fragments into smaller, denser clumps, each destined to become a star. As these clumps continue to contract, their cores become increasingly hot and dense. The atoms within the core collide with increasing frequency and velocity, generating heat and pressure that resist further gravitational collapse. When the temperature and pressure at the core of a collapsing clump reach a critical threshold, nuclear fusion ignites. Under these extreme conditions, hydrogen atoms fuse to form helium, releasing an enormous amount of energy. A star is born. Once a star achieves nuclear fusion in its core, it enters a long, stable period known as the main sequence. This phase constitutes the majority of a star's lifespan, during which it steadily fuses hydrogen into helium in its core, generating the energy that makes it shine. Our sun is currently in its main sequence, having been in this stage for about 4.6 billion years. The length of a star's main sequence lifetime is determined primarily by its mass. Massive stars have much shorter lifespans, burning through their hydrogen fuel at an accelerated rate. Smaller stars, on the other hand, have lower core temperatures and pressures, resulting in a much slower rate of nuclear fusion. These stars can persist on the main sequence for billions or even trillions of years. The relationship between a star's mass, luminosity, and temperature is a fundamental principle in astrophysics. As a star ages, it gradually consumes the hydrogen fuel in its core. Eventually, the core becomes dominated by helium, the byproduct of hydrogen fusion. With hydrogen fusion no longer occurring in the core, the outward pressure that once balanced gravity diminishes. The core contracts under its own weight, causing its temperature and pressure to soar. This increase in core temperature and pressure ignites helium fusion, causing the star to expand dramatically. The star swells to an enormous size, becoming a red giant, or in the case of the most massive stars, a red supergiant. The outer layers of a red giant or supergiant are loosely bound by gravity and are gradually ejected into space, forming a planetary nebula. The fate of a star's core after it ejects its outer layers depends on its initial mass. Lower mass stars will leave behind a white dwarf, while more massive stars may form neutron stars or black holes. For stars like our sun and those less massive, the journey ends with the formation of a white dwarf. After shedding its outer layers as a red giant, the core of the star, now depleted of nuclear fuel, is exposed. This core, composed primarily of carbon and oxygen, is incredibly dense, packing a mass comparable to the Sun into a volume roughly the size of Earth. White dwarfs are no longer supported by nuclear fusion. Instead, they are held up by a quantum mechanical effect known as electron degeneracy pressure. Despite their hot temperatures, white dwarfs are incredibly faint. Over billions of years, white dwarfs slowly cool down, fading from view as they radiate away their residual heat. Eventually, they will become black dwarfs, cold, inert remnants of their former stellar selves. For stars significantly more massive than our Sun, the core collapse at the end of their lives is far more dramatic. As the core collapses, it crushes the atoms within, forcing electrons and protons to combine and form neutrons. The result is a neutron star, an object even denser than a white dwarf, packing a mass greater than the Sun into a sphere only about 20 kilometers across. Neutron stars are exotic objects with extreme properties. Some neutron stars rotate rapidly, emitting beams of radiation from their poles. If these beams happen to sweep across Earth, we observe them as pulsars, celestial objects that appear to blink on and off with incredible regularity. Neutron stars are also associated with some of the most energetic events in the universe, such as kilonovas. For the most massive stars, the core collapse at the end of their lives is so extreme that nothing can stop it. The core continues to collapse indefinitely, forming an object of infinite density and zero volume, known as a singularity. This singularity is surrounded by a region of space-time where gravity is so strong that nothing, not even light, can escape, a black hole. Black holes are among the most enigmatic objects in the universe. They are defined by their event horizons, boundaries beyond which nothing can return. Anything that crosses the event horizon is inexorably drawn toward the singularity at the center of the black hole. Supermassive black holes, millions or even billions of times more massive than our Sun, lurk in the centers of most galaxies, including our own Milky Way. While white dwarfs, neutron stars, and black holes represent the end states of stellar evolution, the processes that lead to their formation can be incredibly dramatic. For massive stars, the death throes are marked by a cataclysmic explosion known as a supernova. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. There are two main types of supernovae, Type 1 and Type 2. Type 1 supernovae occur in binary star systems where a white dwarf is accreting matter from a companion star. Type 2 supernovae occur when a massive star runs out of nuclear fuel and its core collapses under its own gravity. The intense energy released in these explosions disperses heavy elements throughout interstellar space. These elements eventually become incorporated into new stars and planetary systems, enriching the chemical diversity of the cosmos. Stars are not only sources of light and heat, they are also cosmic alchemists, transforming matter and creating new elements in the process. Nuclear fusion, the process that powers stars, is responsible for this cosmic alchemy. Throughout their lives, stars fuse lighter elements into heavier ones, enriching the chemical diversity of the universe. The most massive stars can fuse elements up to iron in their cores. The intense heat and pressure of a supernova explosion can create even heavier elements such as gold, platinum, and uranium. These elements are dispersed into interstellar space, enriching the material from which new stars and planets will form. Star life cycles are not isolated events. They are intimately connected to the evolution of galaxies, the vast cosmic structures that house billions of stars. The birth, life, and death of stars drive the dynamic processes that shape galaxies over cosmic timescales. Supernova explosions inject enormous amounts of energy and heavy elements into the interstellar medium. These explosions can trigger the formation of new stars, enriching the chemical composition of galaxies over time. The cycle of starbirth, life, and death drives the chemical evolution of galaxies, gradually increasing their metallicity. The intricate dance of stars within galaxies creates the diverse and ever-changing cosmic tapestry we observe today. As we conclude our journey through the epic life cycles of stars, it's awe-inspiring to reflect on our place in this grand cosmic scheme. We are, after all, stardust. The atoms in our bodies were forged in the hearts of stars that lived and died billions of years ago. Every breath we take, every object we touch, carries the legacy of these ancient stellar furnaces. By understanding the lives and deaths of stars, we gain insights into the fundamental laws of physics and our connection to the universe. As we continue to explore the universe, unraveling the mysteries of stars, we embark on a journey of self-discovery, tracing our origins back to the fiery crucibles where it all began. If you enjoyed this journey, subscribe for more stellar adventures and cosmic insights.